in this session we describe and discuss this analysis of variance and covariance. Let us discuss about this analysis of variance first. And the analysis of variance is abbreviated as ANOVA, and this technique is used when multiple sample cases are involved. The significance of the difference between the means of two samples can be judged through either Z-test or the T-test. But the difficulty arises when we happen to examine the significance of the difference amongst more than two sample means at the same time. The ANOVA technique enables us to perform this simultaneous test, and as such is considered to be an important tool of analysis in the hands of a researcher. Using this technique, one can draw inferences about whether the samples have been drawn from populations having the same mean. The ANOVA technique is important in the context of all those situations where we want to compare more than two populations, such as in comparing the yield of crop from several varieties of seeds, the gasoline mileage of 4 automobiles, the smoking or drinking habits of 5 groups of university students, and so on. In such circumstances, one generally does not want to consider all possible combinations of two populations at a time, for that would require a great number of tests before we would be able to arrive at relation. This would also consume a lot of time and money, and even then, certain relationships may be left unidentified. Therefore, one quite often utilizes the ANOVA technique, and through it investigates the differences among the means of all the populations simultaneously. Professor R.A. Fisher was the first man to use the term variance, and in fact it was he who developed a very elaborate theory concerning ANOVA, explaining its usefulness in practical field. And we all know that standard deviation is equal to square root of variance. The essence of ANOVA is that the total amount of variation in a set of data is broken down into two types: that amount which can be attributed to chance and that amount which can be attributed to specified causes. There may be variation between samples and also within samples items. That means the items within a sample there may be variation, and there may be variation between samples. ANOVA consists in splitting the variance for analytical purposes. Hence, it is a method of analyzing the variance to which a response is subject into its various components corresponding to various sources of variation. Through this technique, one can explain whether various varieties of seeds or fertilizers or soils differ significantly, so that a policy decision could be taken accordingly concerning a particular variety in the context of agricultural researches. Similarly, the manager of a big concern can analyze the performance of various salesmen of his concern in order to know whether their performances differ significantly. In fact, this ANOVA as a technique is used in many fields, and here some fields are mentioned: economics, biology, education, psychology, sociology, business, industry, manufacturing, and in researches of several other disciplines. In this session, let us try to understand how we conduct this ANOVA by means of certain examples. And here in ANOVA, we have one-way ANOVA, two-way ANOVA, three-way ANOVA, or we can say more-way ANOVA. If we take only one factor and investigate the differences amongst its various categories, having numerous possible values, we are set to use one-way ANOVA. And in case we investigate two factors at the same time, then we use two-way ANOVA. That means when we consider one factor, it is considered as one-way ANOVA. If we consider two factors at the same time, then it is called two-way ANOVA. In a two-way ANOVA or more-way ANOVA, the interaction means the interrelation between two independent variables or factors, if any, between two independent variables affecting a dependent variable can as well be studied for better decisions. The basic principle of ANOVA is to test for differences among the means of the populations by examining the amount of variation within each of these samples relative to the amount of variation between samples. We have to consider here two variations: variation within each of the samples and variation between the samples. In terms of variation within the given population, it is assumed that the values of Xij differ from the mean of this population only because of random effects. That is, there are influences on Xij which are unexplainable. Whereas in examining differences between populations, we assume that the differences between the mean of the jth population and the grand mean is attributable to what is called a specific factor, or what is technically described as treatment effect. Thus, while using ANOVA, we assume that each of the samples is drawn from a normal population and that each of these populations has the same variance. We also assume that all factors other than the one or more being tested are effectively controlled. Thus, in other words, we assume the absence of many factors that might affect our conclusions concerning the factors to be studied. In short, we have to make two estimates of population variance, one based on between sample variance and the other based on within samples variance. Then the said two estimates of population variance are compared with F test, wherein we work out F equal to estimate of population variance based on between samples variance divided by estimate of population variance based on within samples variance. And this value of F is to be compared to the F limit for given degrees of freedom. If the F value we work out is equal or exceeds the F limit value to be seen from F tables, we may say that there are significant differences between the sample means. Now let us discuss ANOVA technique, particularly the one way. We start with one way ANOVA. That means we consider a single factor, only one factor, and then observe that the reason for the said factor to be important is that several possible types of samples can occur within that factor. And we then determine if there are differences within that factor, and the procedure is given here. And obtain the mean of each sample, work out the mean of the sample means, then take the deviations of the sample means from the mean of the sample means and calculate the square of such deviations, which may be multiplied by the number of items in the corresponding sample, and then obtain their total. That is actually this sum of squares for variance between the samples. This is here, SS between. Here, N1 is the number of items in the first sample, N2 is the number of items in the second sample, Nk is the number of items in the kth sample. And here, X1 bar is the mean of items in the first sample. Like that we can discuss. And then divide the result of this third step by the degrees of freedom between the samples to obtain variance or mean square between samples. This mean square between samples, that is given as ms between equal to ss between by k minus 1, where k minus 1 represents the degrees of freedom between samples. Then similar to this ss between, we calculate ss within like this. Then divide the result of this ss within by the degrees of freedom within samples. So ms within, that is ss within by n minus k, where k is the number of samples and n is total number of items in all the samples. And then ss for total variance. This is done for a check, that the sum of squares of deviations for total variance can also be worked out by adding the squares of deviations when the deviations for the individual items in all the samples have been taken from the mean of the sample means. This is given by this. And in fact, SS for total variance, this is equal to SS between plus SS within. That means this SS between plus this SS within. This is giving us SS total, SS for total variance. That is what you explained here. SS for total variance equal to SS between plus SS within. And the degrees of freedom for total variance will be equal to number of items in all samples minus 1. That is n minus 1. These are the degrees of freedom for this total variance. And whereas k minus 1 is related to this SS between and n minus k is related to SS within. And then finally F ratio is calculated as MS between by MS within. And this ratio is used to judge whether the difference among several sample means is significant or is just a matter of sampling fluctuations. For this purpose, we look into the table given in the appendix of this book, giving the values of F for given degrees of freedom at different levels of significance. If the worked out value of F is less than the table value of F, the difference is taken as insignificant. That is due to chance only. And the null hypothesis of no difference between sample means stands. In case the calculated value of F happens to be either equal or more than its table value, the difference is considered as significant, which means the samples could not have come from the same universe, and accordingly the conclusion may be drawn. The higher the calculated value of F is above the table value, the more definite and sure one can be about his conclusions. Now, how to set up this ANOVA table? This table is explaining this, whatever we have discussed so far, that is summarized here. Then there is a shortcut method for one-way ANOVA. This we will see later. And the results by the direct method as well as this shortcut method, they will be same. So any of these methods, that means either direct method or shortcut method you can use. Now we explain this ANOVA by means of an example, that is illustration 1. Set up an analysis of variance table for the following per acre production data for 3 varieties of wheat, each grown on 4 plots, and state if the variety differences are significant. Here, 3 varieties of wheat. So variety of wheat, that is a factor. Wheat variety is a factor, and so this is one-way ANOVA. So there are now 3 varieties of wheat, A, B, C, and 4 plots of land are there. So first variety A is sown in these 4 plots, and then production from this plot 1 is 6 units per acre, and in the plot of land 2, the output or the production is 7 units per acre, and here 3 units per acre and 8 units per acre corresponding to the 4th plot. Now the B variety of wheat, when it is sown in these 4 plots of land, the production is like this, 5537 units. And when C variety of wheat is sown in 4 plots of land, then the production is 5 units, 4 units, 3 units, 4 units per acre. Now, how to set up this ANOVA table? We follow the same steps which are given in the previous pages. We can solve this problem by the direct method or by shortcut method, but in each case we shall get the same result. And here both the methods are shown. Now, solution through direct method. Now, you see this data, and we calculate the mean of each of these samples. Now, sample A, sample B, and sample C. Sample A, here we say 4 items are there, and here sample B 4 items, sample C 4 items. And what is the mean of the first sample? That is 6 plus 7 plus 3 plus 8 divided by 4, that is 6. The mean of sample 2, 5 plus 5 plus 3 plus 7 by 4, 5. Mean of sample C, 5 plus 4 plus 3 plus 4 by 4. These are x1 bar, x2 bar and x3 bar. Then mean of the sample means, or we say grand mean here, that is equal to x1 bar plus x2 bar plus x3 bar by k, and here 6 plus 5 plus 4 by 3, so 5. This is mean of the sample means denoted by x double bar. Now we work out SS between and SS within samples. SS between, that is by this equation, n1 into x1 bar minus x double bar whole square plus n2 into x2 bar minus x double bar whole square plus n3 into x3 bar minus x double bar whole square. Now n1, the number of items in the first sample 4, and x1 bar is 6, and x double bar, that is mean of the sample means, that is 5. So 4 into 6 minus 5 whole square plus n2 is again 4 and x2 bar is 5, as shown here, 5, and minus x double bar 5 whole square plus n3, here in this case n3 is also 4 and x3 bar is 4 and x double bar is 5. So we have calculated here SS between as 8. Now SS within, that is given by this equation. Accordingly, what we do, this 6, 7, 3, 8, this column, 6, 7, 3, 8, and each value is subtracted from x1 bar. That means 6 here, x1 bar is 6, 6, 7, 3, 8. These are corresponding to the sample 1. So these values are subtracted from that first sample mean of 6. And now coming to this second sample, here 5, 5, 3, 7, and its mean is 5. So now we have 5, 5, 3, and 7, and these are subtracted from their mean value of 5. And then we have the third sample containing 4, 5, 4, 3, 4. So we have here 5, and then 4, 3, and then 4, and they are subtracted from the respective mean of 4. That is x3 bar is 4. Yes. So this way we have calculated SS within samples, that is 24. SS between samples is 8 and SS within samples is 24. And then SS for total variance. And SS for total variance, this can be said as a check. That is sigma xij minus x double bar whole square. Here what we have done, we have taken all the elements and we have subtracted from the mean of means. Here you can see 6, 7, 3, 8. Here 6, 7, 3, 8. Then 5, 5, 3, 7. Then 5, 4, 3, 4. These are subtracted from the mean of mean, that is 5. Then this is squared and summed up. This value is 32. Now you can observe clearly that SS for total variance, this 32 is equal to SS between plus SS within. SS between is 8 and SS within is 24. You can see here. SS within 24 and SS between, that is 8. Now we can set up the ANOVA table. What we have done, source of variation and SS values, degrees of freedom, and here mean square value, and then F ratio, and then 5% F limit from the F table. And MS values, how to calculate, we have already seen here. Mean square values, how to do it. Here it is already tabulated. So following that procedure, we are now setting up the ANOVA table. Now between samples, so SS between samples, that value is 8, because SS value between, that is 8, and SS within, that is 24. So SS within 24 and SS total, that is 32, we have seen here. So this 32. Then degrees of freedom. Here degrees of freedom, here we can see there are 3 varieties. So 3 minus 1. And here it is n minus k. N value is 12 and k value is 3. So this is 9. And then total, here degrees of freedom will be n minus 1. N is 12 and yes, n minus 1, 12 minus 1, 11. And if you see here, this 2 plus 9, that is 11. Regarding this degrees of freedom also, if you want to confirm yourself, just have a look at this table. It is already given here. That is between samples k minus 1, within samples n minus k, and total n minus 1. That is what we have done now. And after doing this, we have these mean square values. These mean square values are calculated like this. This SS value between samples 8 divided by the corresponding degrees of freedom 2. 8 by 2, 4. And here within sample SS is 24 and here degrees of freedom 9. So MS is 24 by 9, that is 2.67. After calculating these MS values for between samples and within samples, we calculated the F ratio. F ratio is this 4 by 2.67, that is 1.5. And now this calculated value of 1.5 is compared with the F value at 5% level of significance from the table corresponding to that 2 and 9. 2 and 9 means this 2 degrees of freedom and 9 degrees of freedom. We take this as V1 and this as V2. And let us see the F table. If we see the F table, yes, critical values of F distribution at 5%. V1 2, V1 2, and V2 9. V2 9. So corresponding F value is 4.26. 4.26. So here it is written as 4.26. And now we will compare this calculated value of F with this table value. And this calculated value 1.5 is much less than this value obtained from the table, that is 4.26. Calculated value of F is 1.5, which is less than the table value of 4.26 at 5% level, with degrees of freedom being V1 equal to 2 and V2 equal to 9, and hence could have arisen due to chance only. There are no specific factors. This analysis supports the null hypothesis of no difference in the sample means. We may therefore conclude that the difference in wheat output due to varieties is insignificant and is just a matter of chance. So this conclusion can be made. And later the author has solved the same problem using the shortcut method. If you are interested, you can go through this. This is also simpler. And the results will be same as the results obtained by the direct method. Then coming to two-way ANOVA. Two-way ANOVA technique is used when the data are classified on the basis of two factors. Here we are considering two factors. For example, the agricultural output may be classified on the basis of different varieties of seeds and also on the basis of different varieties of fertilizers used. That means here one factor is varieties of seeds and another factor is varieties of fertilizers. So two factors are considered. Then it will be called as two-way ANOVA. And another example is given. A business firm may have its sales data classified on the basis of different salesmen and also on the basis of sales in different regions. If we come to a factory, the various units of product produced during a certain period may be classified on the basis of different varieties of machines used and also on the basis of different grades of labor. In this particular case, different grades of labor is one factor, and the varieties of machines, different variety of machines is another factor. Such a two-way design may have repeated measurements of each factor or may not have repeated values. We have two different procedures for this, when there are repeated values and when there are no repeated values. The ANOVA technique is little different in case of repeated measurements, where we also compute the interaction variation. And where the values are repeated, then we also compute the interaction variation. And of course, now we will discuss both the cases when repeated values are not there, as case A, and case B contains the repeated values. Now, to discuss this case A, we have to discuss these steps also. Like there are correction factors and squares of all the items one by one and then take its total. So this procedure is given to obtain SS between rows, and here total SS minus SS between columns plus SS between rows. That means these two terms in brackets. That will be equal to, when these two are put together and subtracted from total SS, we get SS for residual or error variance. Then degrees of freedom can be worked out as under. Degrees of freedom for total variance is given as CR minus 1. Degrees of freedom for variance between columns is given as C minus 1, between rows as R minus 1. For residual variance, C minus 1 into R minus 1, where C is the number of columns, R is the number of rows. And ANOVA table, this is the structure of this ANOVA table for two-way ANOVA. Between columns treatment, sum of squares, those are calculated like this. In between rows treatment like this. Then residual error, that is calculated by this. Then total. Then degrees of freedom for this between columns treatment, between rows treatment, for this residual or error, then total. And the mean square, that is calculated like this. And F ratio is calculated like this. And now let us discuss this two-way ANOVA by means of an example. This is illustration 2. Set up an analysis of variance table for the following two-way design results. Per acre production data wheat in metric tons. Here units are in metric tons. Now we can see here there are 3 varieties of seeds, A, B, C, and 4 varieties of fertilizers, W, X, Y, Z. And how it can be understood? When variety of seed A is used with the fertilizer W, then 6 metric tons is the production per acre. And when B is used with fertilizer W, then 5 metric tons is the production per acre. When C variety of seed is used with fertilizer W, then 5 metric tons is the production there per acre. And here this is 7, this indicates 7 metric tons per acre. This is the production when A variety seed with fertilizer variety X is used. Like that we can understand this table. Now, in addition to setting up this ANOVA table for these following two-way design results, but we have to state whether variety differences are significant at 5% level or not. Let us see. Now, that solution is given here. Computations for two-way ANOVA in a design without repeated values. Now, total, here T is given as 60 and N is 12. And what is this T is equal to 60? You can get from here. You make up the summation of this data. That is 6 plus 5 plus 5 plus 7 plus 5 plus 4 plus 3 plus 3 plus 3 plus 8 plus 7 plus 4. That is total is capital T. That is 60. And n is 12 because this data total 12. And there are total 4 rows and 3 columns, total 12. And then the correction factor is calculated as T square by n. 60 square by 12, that is 300. Now total SS. Total SS is calculated like this. That means here that equation is already given. This 36, 25, 25 means this. This one. All these are squared and summed up. Like this. 6 square plus 5 square plus 5 square plus 7 square plus 5 square plus 4 square plus 3 square plus 3 square plus 3 square plus 8 square plus 7 square plus 4 square. So that is what here. All this minus our correction factor. So then that is equal to 32. Then this is about total SS. Now SS between columns of treatment. SS between columns of treatment, how they have obtained here. 24, how this is 24? This is like this. You make this summation of this column. 6 plus 7 plus 3 plus 8. This is 24. So 24 square divided by the number. Total is 4. And then here this 5 plus 5 plus 3 plus 7. 20. So 20 square by 4. And 5 plus 4 plus 3 plus 4. 16. 16 square. That is 16 square by 4. So minus this correction factor. That is 300. So when we do that, we have got this 8. So SS between columns treatment is 8. And now SS between rows treatment. And here 16, 16, 9 and 19. How we have obtained, you can see now here. 16 means actually this summation, row summation. 6 plus 5 plus 5, so 16. That's square and divided by, here you can observe, 3 because there are 3 values only. And next also 16 only, 7 plus 5 plus 4. This is 16, so 16 into 16 by 3. Then here it is 9 total. So 9 into 9 by 3. And here it is 19. So 19 into 19 by 3. Minus the correction factor. So here we have got 18. That is SS between rows treatment. Then SS residual or error. That is given as total SS minus half this SS between columns plus SS between rows. The total SS is 32 and minus of this 8 plus 18. So that is now 6. SS residual or error, that is 6. And then now we have this Anova table. Between columns, that SS is 8. Between rows, it is 18. Residual or error 6. Just now we have seen it. This is 6, this is 18, and this is 8. And their degrees of freedom. And as there are 3 columns, C minus 1, 3 minus 1, 2. Here, number of rows are 4. So 4 minus 1, 3. And residual error, C minus 1 multiplied by R minus 1. 3 minus 1 into 4 minus 1. It is 2, 3, 6. Then total. Total we have seen as SS 32. And here CR minus 1. C is 3, R is number of rows 4. So 12 minus 1, that is 11. Now coming to this MS value. This MS value here, this SS by this degrees of freedom. So 8 by 2, 4. Here 18 by 3, 6. And here 6 by, here this 6 by this 6. That is 1. MS values are calculated. Now F ratio. How we calculate this F ratio? This 4 divided by this 4 divided by this 1, that is 4, and then here 6 by this 1, this is 6. So these are F ratios calculated. Now actually between columns means between varieties of seeds, between rows means between varieties of fertilizers. Now F ratios are calculated here. Now what about this from the F table? And we have to find out the critical value of F corresponding to 5% level of significance. And V1 here it is say 2, and then V2 we take this 6, 2, 6, and corresponding to this V1 V2 values, what is our this and degrees this V1 equal to 2 and V2 equal to 6, and corresponding to 5% level of significance. We see V1 equal to 2 and V2 equal to 6. The value is 5.14. So that is written 5.14. And here corresponding to this 3 and then this 6. And V1 3 and V2 6. V1 3 and V2 6, then corresponding 4.276. So that 4.76 value is written here. And now we have to make a comparison. This F ratio 4 is to be compared with 5.14, and this 6 is to be compared with 4.76. Here what can be observed? Here is an important observation, that is between varieties of seeds, the sources of variation, if we consider this calculated value of F ratio is less than the critical value of 5.14 for the given 5% level of confidence. But here, this for sources of variation, that is between varieties of fertilizers, the calculated value of F ratio is more than the critical value from the table, that is 4.76. So from this, what we can conclude, that is this one. From the said Anova table, we find that the differences concerning varieties of seeds are insignificant at 5% level, as the calculated F ratio of 4 is less than the table value of 5.14. But the variety differences concerning fertilizers are significant, as the calculated F ratio of 6 is more than its table value of 4.76. So this is our conclusion. And now coming to the case of case B, Anova technique in context of two-way design when repeated values are there. In case of a two-way design with repeated measurements for all of the categories, we can obtain a separate independent measure of inherent or smallest variations. For this measure, we can calculate the sum of squares and degrees of freedom in the same way as we had worked out the sum of squares for variance within samples in the case of one-way Anova. Total SS between columns and SS between rows can also be worked out as stated above. We then find leftover sums of squares and leftover degrees of freedom, which are used for what is known as interaction variation. So here is the difference when repeated values are there. After making all these computations, Anova table can be set up for drawing inferences. And now one example is taken to demonstrate that. This illustration 3. Set up Anova table for the following information relating to the 3 drugs testing to judge the effectiveness in reducing blood pressure for 3 different groups of people. Here groups of people mean A, B, C. There are 3 groups of people and 3 varieties of drugs are there. Drug X, drug Y and drug variety Z. And here varieties of drug is one factor and these varieties of people or different groups of people. Different groups of people, this is another factor. And so there are two factors. It is a two-way ANOVA. Here the point to be noted is here the values are actually here repeated values are there. If we take this group of people A, XYZ values, and when X drug is executed on group of people A, the reduction in blood pressure is 14 units. And the same X is used repeatedly on the same group of people A, then the reduction in blood pressure is observed as 15 units. Here we can understand when drug Y is used on this group of people A, 10 units of blood pressure is reduced. But when the same drug Y is used on the same group of people A repeatedly, then that means second time, then reduction in blood pressure is 9 units. Now here we can understand that when Z drug is used on the same group of people A, then 11 units of blood pressure reduction, and when it is repeated again on the same group of people, then reduction in blood pressure is 11 units. And similarly we can understand these values. When XYZ are given to this group of people B, these are the reduction in the blood pressure units. And when those are repeated on the same group of people B, then these are the reductions in the blood pressure. And here it is, these are related to the group C, when XYZ are employed on them. And when repetition is done, that means when these drugs XYZ are given to the same group of people C, then the reduction in blood pressure in units, these are given here. Now the questions are, do the drugs act differently? Are the different groups of people affected differently? Is the interaction term significant? Answer the above questions taking a significant level of 5%. Here it is the case of this ANOVA technique in context of two-way design when repeated values are there. And in this case, in addition to our total SS, SS between columns and SS between rows, we find out leftover sums of squares and leftover degrees of freedom, which are used for what is known as interaction variation. Interaction is the measure of interrelationship among the two different classifications. Now, how this ANOVA table is set up, we see now. Yes. Now, total T equal to 187 and N is equal to 18. What is this 187? You can, that is actually the summation of all these values. Of course, you ignore this B and C, these numerical values. This total summation, that is equal to 187. And how many data points are there? Total 18. Here 6, 6, 6. Total 18. So N equal to 18. N equal to 18 and T is 187. So that's the correction factor, T square by N. That is now calculated as 1942.72. Then total SS. Total SS, as I have already discussed, 14, 15, 12, 11. How they are, you can observe here. Here, this is corresponding to this. 14, 15, 12, 11, 10, 11. And here 10, 9, 7, 8, 11, 11. 11, 11, 10, 11, 8, 7. And all those are squared. And then minus of this correction factor. So the value is 76.28. Then SS between columns. SS between columns means between drugs. And that is 73. How this 73 is there, you can make this column summation. 14 plus 50, yes, 29, 31, 41, 42, 52, 62, 63, 73. So that 73 value is written here. Then coming to the second column related to drug Y, this is 19, 26, 34, 35, 45, 46, 56. And here this is 22, 32, 33, 43, 51, 58. So that 58. And total number of values, those are 6. So minus that correction. So this is 28.77. SS between rows, that is 70, 59 and 58. How those are there you can see here. Rows means this one. This you make the summation. 24, 25, 35, 59, 70. And number of values, these are 6. And here 19, 29, 30, 48, 49, 59. And here 29, 30, 40, 51, 58. The same way. So it is done this way minus that correction. So SS between columns, that is between drugs, is this. SS between rows, yes, here. SS between rows, we have done this as 14.78. Then SS within samples. Actually here we are calculating for this repeated measurements. SS within samples and SS for interaction variation. SS within samples, how we are doing. Here you can see 14 and minus 14.5. So how this is done you can see here. Here you see this is 14 and this is 15. So average is taken as 14 plus 15 by 2. That is 14.5. That 14.5 is subtracted from this 14 as well as this 15. And here this 10 and 9. And the average is 9.5. That 9.5 is subtracted from this 10 as well as from 9. Here 11 and 11, average is 11 only. So that 11 is subtracted from this 11 and from this 11. And here 12 and 11, average is 11.5. That 11.5 is subtracted from 12 and 11. Here average is 7.5. That is subtracted from this 7 and 8. Here average is 10.5. That is subtracted from 10 and 11. And here average is 10.5. That is subtracted from 10 and 11. The average is 11. That is subtracted from 11 and 11. The average is 7.5. That is subtracted from 8 and 7. So that way it is done here. It is done that way and squared up and summed. So this SS within samples is 3.5. Then SS for interaction variation. How that is obtained, you see, SS total 76.28. That is written here. Minus SS between columns 28.77. And then here 14.78 is related to SS between rows. And SS within samples 3.5. So from this we have got SS for interaction variation 29.23. Now we are setting up the ANOVA table. ANOVA table is set up like this. Now between columns, that is between drugs, SS value 28.77, that we have seen already. And between rows, that is 14.78. And then this 3.5 related to within samples, that is error. Then interaction, that is 29.23, that we have seen here, 29.23. And this SS within samples, this is also called error. That error value is 3.5. And okay. Now coming to our discussion, the degrees of freedom. Here number of columns are 3. So C minus 1. 3 minus 1, that is 2. And number of rows 3 only, because 3 groups of people, that is here A, B, C, and basically 3 groups of people only, so 3 minus 1, that is 2. And then coming to our this interaction, here it is 4, and within samples 18 minus 9, that is 9, and total is that n minus 1. n minus 1, that is 17. And here this interaction and how these degrees of freedom are arrived at, you can refer to this table. Okay, here this is basically for our this, when repeated values are not there, but on similar lines we can understand how this ANOVA table is set up in this case. Okay. Here c minus 1 r minus 1, and here it is n minus 1, and here coming to our yes, as there are 3 rows and 3 columns, then within samples the degrees of freedom will be 9. Okay, and then this here it is 2, here it is 2, and here it is 9, and 2 plus 2 plus 9, 13, and then 17 minus 13, 17 minus 13, that is 4. So 4 degrees of freedom for interaction is calculated like this. That is totally 17. From this 17, this 9 plus 2 plus 2, those are subtracted. So interaction degrees of freedom calculated as 4. Here, I think it is given here. Interaction degrees of freedom 17 minus of 2 plus 2 plus 9, that is 4. Okay. And now coming to our MS values, and this is SS by degrees of freedom 28.77 by 2, and here 14.78 by 2, and here 29.23 by 4, 3.5 by 9, and then we have F ratio calculation, and for F ratio calculation we take this MS 14.385 divided by that error MS value corresponding to error, that is 0.389. So 14.385 by 0.389, that is 36.9. And for F ratio between rows, that is between people, 7.390, this 7.390 divided by MS value corresponding to that error, 0.389, it is 19. And then coming to this interaction here, this value 29.23 by 4, that is equal to 7.308, that divided by this MS value corresponding to this error, 0.389. Of course calculated value is not shown, and but that will be definitely more than this tabular value. And yes, after this we compare these calculated values of F ratio with the F values we get from the table for 5% level of significance. And here the F ratio is 36.9. It is much greater than the tabulated value. How this tabulated value is found out? That is simple, because V1 is 2, and this 9 we have taken corresponding to this error. So 2 and 9. And then similarly for this between rows, degrees of freedom 2, and then degrees of freedom for this error 9. So this value is also 4.26. And here the calculated value of F ratio is much higher than this tabulated value of 4.26. And here also, as I said, this interaction, F ratio corresponding to this interaction, this here will be also much higher than this 3.63. That means the calculated values of F ratio, those are all higher than the tabulated values. So we say that these three F ratios means F ratio corresponding to between columns, between rows, and the interaction. Those are very significant. So what we can say, that means that the drugs react differently, and different groups of people are affected differently, and the interaction term is significant. So this is our conclusion. We don't say that drugs react in the same manner or similar manner, and different groups of people are not affected differently. We can't say that, because all these three F ratios are more than these tabulated values. So this conclusion is right, that drugs act differently, different groups of people are affected differently, and the interaction term is significant. In fact, if the interaction term happens to be significant, it is pointless to talk about the differences between various treatments. That is, differences between drugs or differences between groups of people in the given case. And now they have drawn a graph also. Here XYZ, these are the drugs, and blood pressure reduction in millimeters of mercury, that is shown. A is indicated by solid line, and this line, this dashes, this small dashes line is corresponding to B, and this long dashes, those are corresponding to C. In fact, here is the interaction. You can see that this and this, they are interacting, and similarly this B and then this C, they are also now cutting here. What we can conclude, if the connecting lines do not cross over each other, then the graph indicates that there is no interaction. But if the lines do cross, which is the case now, they indicate definite interaction or interrelation between the two factors. This is the conclusion which we can make. And when we have drawn such a graph, then we can also observe this. The highest reduction in the blood pressure in case of C is with the drug Y, and the lowest reduction is with the drug Z. Whereas highest reduction in blood pressure in case of A and B is with drug X, and the lowest reduction is with the drug Y. Thus there is definite interrelation between the drugs and the group of people, and one cannot make any strong statements about drugs unless he qualifies his conclusions by stating which group of people he is dealing with. In such a situation, performing F tests is meaningless. But if the lines do not cross over each other and remain more or less identical, then there is no interaction, or the interaction is not considered a significantly large value, in which case the researcher should proceed to test the main effects, drugs and people in the given case, as stated earlier. And we stop here, and then we try to discuss about the exercise problems. Those are named as questions at the end of this chapter. Let us go ahead. Now we discuss these questions. First, A. Explain the meaning of analysis of variance. Describe briefly the technique of analysis of variance for one-way and two-way classifications. This we have already discussed. And state the basic assumptions of the analysis of variance. These basic assumptions also we have discussed. Actually, what we assume that each of the samples is drawn from a normal population, and that each of these populations has the same variance. We also assume that all factors other than the one or more being tested are effectively controlled. This means that we assume the absence of many factors that might affect our conclusions concerning the factors to be studied. So that way you can write the basic assumptions. Then next question is, what do you mean by the additive property of the technique of the analysis of variance? And explain how this technique is superior in comparison to sampling. These all can be explained. Here, additive property of the technique of ANOVA, we have already seen that SS for total variance is equal to SS between plus SS within. And if we consider even the degrees of freedom, SS for total variance degrees of freedom equal to n minus 1. That is the summation of degrees of freedom for SS between k minus 1 and the degrees of freedom n minus k of SS within. Or we say that n minus 1 equal to k minus 1 plus n minus k. That explains the additive property of the ANOVA technique. And how this technique is superior in comparison to sampling, that is given in the beginning itself. And you can also write by your own thinking. Then write short notes on the following. Okay, Latin square design here we are not touching, but we have had a discussion about this Latin square in one of the previous sessions. Then coding in context of analysis of variance. Yes, coding also can be done in some cases, particularly when the data is in such a manner. For example, it is in fact a shortcut method, and this is based on an important property of F ratio, that its value does not change if all the n item values are either multiplied or divided by a common figure, or if a common figure is either added or subtracted from each of the given n item values. Through this method, big figures are reduced in magnitude by division or subtraction, and computation work is simplified without any disturbance on the F ratio. This method should be used especially when given figures are big or otherwise inconvenient. Once the given figures are converted with the help of some common figure, then all the steps of the shortcut method can be adapted for obtaining and interpreting F ratio. And F ratio and its interpretation, yes, you can write. And significance of ANOVA also you can write in your own words. Actually, about all these questions 1, 2, 3, you can give your answers briefly, whatever you think, right? Then coming to this problem number 4, below are the given yields per acre of wheat per 6 plots entering a crop competition. 3 of the plots, here is the printing mistake, it is 3. 3 of the plots being sown with wheat of variety A and 3 with B. This data is given here. This is one way ANOVA, and variety of wheat, that is the factor. And you can follow this illustration 1. This problem is similar to illustration 1. You can set up the table of ANOVA and calculate F. And here some data is already given. The tabulated value of F at 5% level for V1 equal to 1 and V2 equal to 4 is given as 7.71. So you calculate the values of F, and that F value you compare with the tabular value of 7.71. If the calculated value of F is less than 7.71, then then we can follow that the difference between the yields of two varieties is not significant. But if the calculated value is more than 7.71, then you have to say the difference between the yields of the two varieties is significant. And yes, now coming to this fourth question. Yes, this also you can follow a similar procedure. Sixth question is related to the Latin square design that you can. Now coming to this eighth question. three varieties of wheat, W1, W2 and W3, are treated with 4 different fertilizers, F1, F2, F3 and F4. The yields of wheat per acre are as under. Here varieties of wheat, W1, W2, W3, and varieties of fertilizers, F1, F2, F3, F4. So varieties of fertilizers is one factor and varieties of wheat another factor. There are 2 factors. So it is a problem of two-way ANOVA, and you can follow that illustration 2 given in this chapter, which I have already explained, and calculate the F ratios, and those F ratios you can compare with the tabulated values of F, and then you can conclude. Here question is set up a table for the analysis of variance and work out the F ratios in respect of the above. Are the F ratios significant? That will be known only when you calculate these F ratios and compare those F ratios with the tabular values. And here 5% significance level you can take. Even though it is not mentioned, but you can consider 5% or 0.05 as the level of significance, or significance level as 5%. And now coming to this ninth problem. Ninth problem is also like two-way ANOVA, and you can go on in the similar manner. And now coming to this 12th question. Is the interaction variation significant in case of the following information concerning mileage based on different brands of gasoline and cars? Here brands of gasoline, 4 brands are there. There's like 4 varieties. And here cars, A, B, C. But here you can observe that data is repeated. For example, this 4 brands of gasoline, W, X, Y and Z, and used in cars, A. And here the data is the mileage. And here when W is used in car A, 13 is the mileage. But when it is repeated, then 11 is the mileage. And here what we can understand, when gasoline brand X is used in car A, then 12 is the mileage. And when it is repeated, then 10 is the mileage. Like that you can understand. And here you can, whatever you have understood from illustration 3 given in this chapter, the same concept you can apply here, and then you can conclude whether the interaction variation is significant or not. Yes, this completes this unit, ANOVA, Analysis of Variance, and we have discussed 3 problems in the text, and later I have now explained you how to solve these problems, exercise problems, particularly this problem number 4, problem number 5, problem number 8, problem number 9, and problem number 12. I hope you have understood this, and if you have any doubts, you can write to me through email, or even you can contact me on phone. Thank you very much.